Hi. In this video, we'll be talking about how we can encode data using the binary numbering system and why the binary numbering system is so awesome. Remember that the binary number system is a number system with only two digits, 0 and 1. We can represent every number using just zeros and ones if we follow the binary numbering system. Now we call a binary digit a bit. So a bit is a value that can either hold 0 or 1. Every digit in a binary number is known as a bit. Now, why is binary important to computers? Why is this relevant? Well, it turns out that at the base of everything, at the very core level, computers are storing all data in binary. For example, if we look at this code, var x equals the character a, in our heads, what we think about is the variable x holding the value a. And that's totally fine. We can think about the variable x holding the character a in our heads when we program. But in the computer, at the base of everything, at the hardware level, the computer isn't actually storing a symbol that looks like the character A. The computer is actually storing a series of zeros and ones, or rather a series of states of ons and offs that represents the A. It doesn't actually store a character that looks like A. It stores ons and offs, zeros and ones, that encode the A. They represent the A. Now, why would the computer be doing this? Why is it better to use zeros and ones rather than just storing a character that looks like A? Well, it really boils down to being as simple as possible at the hardware level. We don't want to have too much complexity going on when we're storing and reading data. So let's look at the bottom of a CD, for example. Here we see that if you look really closely at a CD, it kind of looks like Braille. It's really just a bunch of bumps and valleys on the surface of the CD. So when the computer is reading this, it can actually read data off of this as zeros and ones. Let's take this little section, for example. When the computer is scanning this CD from left to right, it can see this bump as a 1, this valley as a 0, and this next bump as a 1. Now, what's really happening when a computer reads a CD is a bit more complicated than this, but it really just boils down to this. It's a lot like Braille. The reason we do it this way is imagine if you were the computer and you were trying to get a bunch of data off of the surface of this CD. If you closed your eyes and ran your finger along the surface of this CD, wouldn't it be a lot easier to tell whether your finger is touching a bump or a valley than it would be to tell whether your finger is touching a symbol that looks like an A versus a symbol that looks like a D, for example? It's a lot easier to say, hey, this is a peak, I can interpret this as a 1, this is a valley, I can interpret this as a 0. And what's really cool is we're constantly finding better and better ways to represent lots of ones and zeros. We can do it with bumps on a CD, we can do it with voltages in a circuit, we can do it with high or low frequencies in a radio wave, etc. We're constantly finding new ways to represent ones and zeros. What's cool is no matter how we're representing these ones and zeros on a physical level, the end result on the software level is the same. So how much data can we store using only zeros and ones? Well, we see that it takes a lot of zeros and ones, but it scales up pretty quickly. If we're using just a single bit, just a single 0 or 1, the only value we can represent with that is a true or false, an on or an off. It's either a true or false state. But as soon as we start introducing more bits, we can start to encode more data. For example, 8 bits, or a byte, is how many zeros or ones we need to store a single character of text. It encodes a single character of text. Then we go up to kilobyte, which is 2 to the 10 bytes, or about 1,024 bytes. And that's enough to store a full paragraph of text. Then we move up to megabyte. You've probably seen the word megabyte before. This is 2 to the 20 bytes, and 3 megabytes is how much data it takes to store a 3-minute song. Now we go up to gigabyte. That's 2 to the 30 bytes. To get an idea of how big a gigabyte is, 16 gigabytes is how much storage is on an iPad. So 16 gigabytes can store a lot of data. Now we go up to terabyte. Now we're getting really big. That's 2 to the 40 bytes. Now it only takes 10 terabytes to store the entire Library of Congress. That is huge. And now if we go up to petabyte, that is 2 to the 50 bytes. A single petabyte can store 10 billion Facebook photos. So we see that we can really store a lot of data just using a ton of zeros and ones. Well, how exactly is binary being used to store all this data? If we have 1 bit, like we see, we can only store 2 possible values, 0 or 1. But then if we go to 2 bits, that's doubled. We can now store 4 possible values, 0, 0, 0, 1, 1, 0, and 1, 1. Those are all distinct values. Now if we jump to 3 bits, we double it again. We see that for every one of these values in 2 bits, all we have to do is put a 0 or a 1 in front of it, and we double it. So we see that every time you add a bit, you're doubling the amount of values you can store from the previous number. So n bits can really store 2 to the n possible values, 2 values for each bit. For example, if we look here, in 2 bits, 0, 0, once we go to 3, we can put a 0 in front of that or a 1 in front of that to get 2 brand new values. 0, 1, put a 0 or 1 in front of it to get 2 brand new values. Put a 0 or 1 in front of 1, 0 to get 2 brand new values, and then put a 0 or 1 in front of 1, 1 to get 2 brand new values. So that's how many different values we can store with a given number of bits. But how does that actually turn into the songs or the text that we're reading? Well, all we have to do is define a mapping that maps each possible binary sequence into the actual data that we want to represent. We simply create a table that says, hey, this binary sequence, when read, should be interpreted as this data that I actually want to encode. So for example, I could come up with my own mapping that says 0, 0 should be interpreted as A, 0, 1 should be interpreted as B, 1, 0 should be interpreted as C, and 1, 1 should be interpreted as D. And I've made my own 2-bit custom encoding. The problem with this is I can only represent 4 values, so I'm not getting that much use out of it. I can't make very interesting sentences or very interesting data using only A, B, C, D. The second problem is that no one knows this encoding except for me. If I were to make my own file of zeros and ones that needed to be interpreted this way in order to make sense, I would need the entire world to know about this encoding. And encoding has value once everyone agrees on using it. That way, all machines using this encoding can actually communicate with each other. So what's an example of an encoding that has been agreed upon, that is actually used? Well, one example from history is Morse code. With Morse code, there's 2 different types of signals that we send, a long or a short. A dot is a short signal and a underscore is a long signal. Using this system, we can use any sort of binary stimulus. We can use lights, we can use sound, we can use electric impulses, and we can end up encoding every character in the alphabet. So if we interpret these dots as zeros and these underscores as ones, a 0 means short and a 1 means long. And using the standard Morse code encoding, we can now encode the entire alphabet. Here I'm only showing ABC, but there are sequences that spell out the entire alphabet. So Morse code is an example of a binary communication protocol. It is a protocol because everyone has agreed upon it. And if everyone agrees upon this encoding, then we're actually able to communicate using only 2 different types of signals, long and short, or 1 and 0. Now, computers actually don't use Morse code. This was an old telecommunication protocol when we first started sending telegraphs. What computers use is actually 1 byte, or 8 bits, to store characters. So if we have 8 bits, that's 2 to the 8, or 256 possible values. And that's enough to store every character we would ever want to type. So we simply need to make a full table mapping every possible combination of 8 bits to a corresponding character. So for example, 01000001 could map to A, 01000010 could map to B, and so on. So here we have a mapping that is useful because it maps every character we want to type. But we need a mapping that everyone agrees upon. We need a protocol so that all machines are encoding text the same way. Well, it turns out that protocol already exists. It's called the ASCII table. ASCII just stands for American Standard Code for Information Interchange. Now that acronym isn't so important. What is important is that everyone has adopted this table, this encoding, as a way to encode text. So the ASCII table spells out every binary value that is 8 bits and what character it maps to. So for example, 01000001, which has the decimal value of 65, should be interpreted as an A, and so on. 66 is B, 67 is C, and so whether we're interpreting this as binary, octal, hex, decimal, this is the value that should be interpreted as. So ASCII is a protocol for encoding text. If all machines agree to use the ASCII system, then all machines will be able to correctly interpret text. For example, if we look at this sentence, we can take every 8 bits and that maps to a corresponding character. So if we take all of these, if we take each byte in the sentence and convert it to the corresponding character, we see that this actually says binary is awesome. These zeros and ones turn into the sentence binary is awesome. Let's explore encoding text as binary in the editor. So here we have a tool that interprets bits as data according to an encoding that we define. So right now I have a lot of bits typed out, but it doesn't mean anything. So we see a lot of bugs right here. There's no encoding for 00, there's no encoding for 11. So if we want this to actually map to legitimate data, we can define our own custom encoding here. So let's make our custom 2-bit encoding from earlier. We'll say 00 means A. And we already see that all these zeros are now being interpreted as A's. We can say that 01 should be interpreted as a B. we can say that 1, 0 should be interpreted as a C, and that 1, 1 should be interpreted as D. Awesome, so now all these bits are being interpreted as characters according to our table. What's cool is we can change this to the raw format, so this is how it would actually be stored in a computer. There's no reason to split it up nicely, but if we want to be able to read it, we can click pretty, and we can see there's actually 2 bits per character here. If I want to remove an encoding and change it, I can just cancel this, and let's say I actually want 1, 1 to mean exclamation point now. Great. What's also interesting is we can add more bits. So let's say we actually want change our mind, we want an 8-bit encoding. These bits can remain the same. Let's just say, okay, now we need 0, 0, 0, 1, 1, 0, 1, 1. Let's say that should be A. And now all these 8 bits are now being interpreted as an A. Now these 8 bits, all zeros, 0, 0, 0, 0, 0, 0, 0, 0, let's say that's a B. Great. So we see that it's really up to the software to determine how the hard-coded bits are being determined, and we can define that as we want. The problem is, no one really knows this encoding table. This is just an encoding table that we made up. So if we want to actually encode bits that other computers can read, we need to use the standard encoding. For that, we'll use the ASCII encoding. So here we have a tool that's actually interpreting the raw bits as ASCII. And here you can see the entire ASCII table. It's mapping every sequence of 8 bits to a character. Again, we can interpret it as raw or nice and pretty, 8 bits per line. And we can even display it as binary or hexadecimal. We see that no matter what, the values are the same. It's just how we are viewing them. At the base of it all, it's zeros and ones. Doesn't matter how they're being displayed. The zeros and ones are being interpreted according to the ASCII encoding, and that's what is produced here. So if I wanted to finish this and I want to make it say hi there, all I need to do is type out an E. So let's see what an E is. An E is this. Great. Let's add an exclamation point too. There's exclamation. Doesn't matter how many new lines I put, it only interprets the zeros and ones. There. Let's say I change this to 20 or 22. I get different types of punctuation. But I want the 21 because that is the exclamation point. So this is a tool that is interpreting a series of bits as ASCII. So we've seen how we can encode a sentence using bits. But what if we receive a sequence of bits? We can also use software to decode that message according to the ASCII table and produce the corresponding text. So here we have a program that's receiving a binary message. It's getting a binary transmission. From there, we decode the message according to the ASCII decode function to produce a text message. Then we print out what that text message is. Problem is this ASCII decode doesn't exist yet. We have to write that. So given a binary message, given a sequence of zeros and ones, how exactly do we turn that into ASCII characters? Well, really all we have to do is grab every chunk of 8 bits. We have to grab every byte of that message, translate that into its decimal equivalent, and then look up that decimal value in the ASCII table to get the corresponding character. So let's make a little roadmap for this function. We're going to return a string. We're going to return a resulting message. So let's initialize that string. Initialize the result string. And then we want to loop over the binary message in chunks of 8 bits. So we should start at 0, then 8, then 16, and so on. So on each iteration of this loop, we want to get the current byte of information. Then we want to get the decimal value of that byte. And then get to the corresponding ASCII value character for that decimal value. And then append that character to the string, to the result string. And then after we loop through the entire message, we should have our full string, so we can return it. Return the result string. So the reason we have to convert it to decimal is because JavaScript provides a nice function that allows us to easily map from decimal to ASCII, and unfortunately does not provide a nice function to map from binary to ASCII. So if we implement every step of this pseudocode that we've laid out, we should have a program that works. So let's go ahead and initialize our result string. Var result string equals the empty string. And we want to loop over the message in chunks of 8. So var I equals 0. I is less than the length of the binary message. And we want to add 8 each time. And inside, we want to do all of this. We want to get the current byte of information. So that byte is going to be the substring, the binary message dot substring, starting at I and ending at I plus 8. Get the decimal value of that byte. We have this nice helper method, binary to decimal, takes a binary string and returns the decimal equivalent. It's just using a nice JavaScript method called parseInt. So var decimal value equals binary to decimal, pass it the binary value, current byte. And now we want the corresponding ASCII character. So var ASCII char is equal to, and this is where JavaScript provides a nice function. It's called string.fromCharCode. It's called string.fromCharCode, and it takes the decimal value. So decimal value as a parameter. And that will convert the given decimal value. It will take the given decimal value and return the ASCII value that corresponds to it. And then we just add that to the result string. And then at the end of the loop, we should have translated the entire binary message so we can return our result string. Let's see if that works. So let's go ahead and copy our message from when we encoded hi there. Let's see if we can decode it. Let's see if we can decode it. Ooh, it had new lines. This is why you have to do raw. Let's see if we can decode it. So let's pass that in. There we go. It correctly translated that binary sequence into hi there. So that is how we can encode text using binary.